Okay, we're going to talk about covalent bonding and Lewis structures in this lecture. I'm hoping you listen to this in replacement of Wednesday night lecture. So Lewis came up with these Lewis dots that we talked about before. And we know that atoms want to have 8 electrons around them except for hydrogen and helium want 2, they want a duet, but everybody else wants to have an octet. And we're going to show bonding by having an electron pair that's shared between 2 atoms. For example, hydrogen has 1 atom apiece, and when each hydrogen bonds together, they share 2 electrons and they make a bond. We can show that with our 2 dots, or we can show it with 1 line. And so we'll start getting used to just showing it with lines in a little while. But right now, let's just do dots. For example, fluorine has 7 valence electrons, and to fill its octet of 8, it can share 2 electrons. And we show it with these electrons here are called unshared pairs of electrons. So fluorine has these 3 sets of unshared pairs, and it's going to share 2 electrons to make that bond. And then every atom feels like it has 8 electrons around it. And so the octet is fine. So this octet rule works really well with carbon, nitrogen, oxygen, and fluorine. And remember, hydrogen wants to have 2 electrons around it. So here's another example of carbon. Has 4 electrons, valence electrons, and fluorine has 7. So if you have 4 fluorines around that central carbon, carbon likes to be in the center of things, then every atom in this structure has 8 electrons around it, and it's happy that way. So we can show it with the dots, or we can start showing it with a line like that. And we'll start getting used to, we'll start out with dots, and then we'll start drawing the 2 electrons shared together as a line. So those are single bonds we just talked about, and now let's talk about double and triple bonds. Some atoms will want to do double bonding or triple bonding, and the way you tell is if you start doing everything with single bonds and you come up with too many electrons or too few electrons, then you have to start doubling up or tripling up the bonding. So to figure it out, you're going to figure out that each oxygen has 6 valence electrons, each carbon has 4, and so we have a total in this molecule of 2 times 6 is 12, plus 4 is 16. And if we drew it with everything with single bonds, that wouldn't come up with 16 electrons. So the way we have it now, we have 8 in the middle, and then we have 8 around the outside, so that makes 16 total. So you always have to come up with the same number of valence electrons as the atoms that come into that bond have. So we can have double bonds, or we can have triple bonds, depending on how many valence electrons we have, and doing that counting to see if we come up with the right number of electrons. But remember, the rule is we have to use all the valence electrons, and we have to make sure that every atom in that structure has 8 electrons around it. So if you look here, this has 4 of the lone electrons, and then it's got 4 bonded together. So this oxygen feels happy, it's got 8 electrons around it. This carbon has 8 around it. It feels totally filled with its octet filled up. And then this oxygen has the 2 unshared pairs of electrons, so that's 4, plus another 4 here, and that's 8. So everybody feels happy this way. So you have to make sure that all the valence number of electrons is taken care of, and every atom has the octet or the duet filled up to be happy. So here, hydrogen has 2 electrons, it's happy. And then carbon has 8 around it, so it's happy. And this nitrogen also has 8 around it, so it feels secure with this octet filled up. Here's some more examples. You can see that every hydrogen has 2 electrons associated with it, and every carbon has 8 associated with it. So they're all filled up with their duet or their octet filled up. And we can draw it with dots, and then later on we're going to draw it with lines like that. To see if we're getting the right Lewis dot structure, we have to do something called formal charges. And it's a way to figure out where electrons are around an atom and whether that structure makes sense. So when we do formal charges, we try to get the lowest possible charge on the structure that we draw. So sometimes there's multiple structures we could draw, and we need to find the one that makes the most sense. So we use formal charges to do that. So what we do is we look at the atom, and then we count how many lone electrons there are, and then we subtract that from its valence number, and we also subtract the number of bonds that we have from it. So for example, this oxygen right here, its valence is 6, and it has 1, 2, 3, 4, 5, 6 items around it, so it's going to have a formal charge of 0. So atoms want to have the smallest number formal charge around that. This oxygen is going to have 1, 2, 3, 4 lone electrons, and then 2 bonds, so that means 6 minus 6 is 0, and so that's oxygen's happy that way too. So let's look at the hydrogen here. Hydrogen has a valence of 1. It's sharing 2 electrons right here, but we just call that a formal charge of 1, so 1 minus 1 is 0, so hydrogen's totally happy. So they're trying to get a real small number for your formal charge. Let's look at the oxygen. Like I said before, we have oxygen is a valence of 6. It's got 4 little electrons not bonding, and then it's got 2 bonds, so 4 and 2 make 6. So 6 minus 6 is 0, so oxygen is happy. So we want to get the smallest numbers possible. So the electron count for oxygen is 6. It has a formal charge of 0 because we did 4 lone electrons and the 2 bonds make 6, so 6 minus 6 is 0, so oxygen has a really low number, and so we're trying to get close to 0. This oxygen, we said, has a formal charge of 0 because it has 4 electrons and 2 bonds, so 6 minus 6 is 0, and so that's a good number. And then this one here, oxygen has a number of 6, and we're subtracting 6 minus the 6 plus 1 is 7, so 6 minus 7 gives it a formal charge of -1. So remember, you use the valence number from the group number, so oxygen is in group 6. So we're going to take that valence number 6 minus these 6, and 1 is 7, so 6 minus 7 is a -1. The nitrogen is in group 5, so it's got 5 minus 1, 2, 3, 4, so it's going to have a formal charge of a +1. So in all the atoms, we're trying to get the smallest numbers possible. So here is the way we show the Lewis dot structure totally complete. And so we need to start doing this. We're going to show our structures with our valence electrons and our bonding, and then we're also going to show the formal charges. So we were trying to get the smallest number possible on our formal charges to have the most stable structure shown. Sometimes molecules can have varying structures, and we want to show the one that's the most stable. So we want the smallest number for formal charges. So the way you do it, remember, is you take the group number minus the number of bonds minus the number of unshared electrons, and that gives you the formal charge number. So when we do Lewis dot structures, let's put in the formal charges. and see if we can get the smallest numbers possible. So here's some, this is a Lewis dot structure that's correct because it has the bonding shown correctly, the unshared electrons properly, and it's got the formal charges shown. So remember, the formal charge has to come up right and show this charge up here as well. So we want to do Lewis dot structures that are correct for what the molecule actually looks like. And so let's go through the steps. So we look at the formula and we try to figure out what's the central atom. And we try to figure out how everything's connected together. Usually carbon wants to be in the center of atoms. And hydrogens are going to be bonded to the carbon. And we count all the valence electrons, and we add those up. And for a neutral atom, it's going to be the valence electrons for all of the atoms in there. If we have a charge, then we have to deal with that separately. But first of all, get all the valence electrons. So for this molecule, we have each hydrogen is contributing 1 electron, each carbon's 4, nitrogen's 5, oxygen 6. So we have a total of 24 electrons we have to show when we make the model, the Lewis structure. We're going to connect the atoms by dashes to show the bonding, or you can show it with 2 electrons like that. So here's the partial structure. We connected everything together, and we think this is the structure. We subtract the electrons in the bonds from the total number of valence electrons. We figured that was 24. So right now you see there's 1, 2, 3, 4, 5, 6 bonds there. So 6 times 2 is 12. So 24 valence electrons minus 12. And then we have to figure out where the rest of those 12 electrons go and make sure that every atom has 8 electrons around it. So we're going to put them in pairs. And we're going to start with the most electronegative atom. So in this one, that's going to be your oxygen. So we're going to add them in pairs, and we're going to try to make every atom happy by having a valence filled up. So in this one, we have 6 electrons left over. We have 6 pairs of electrons left over, so that's 12 electrons. So we put them this way. And if we have we're lacking an octet because nitrogen's not happy this way, then we might have to do a double or triple bond. So in this case, we can do a double bond here, and that makes all of the atoms happy having an octet filled around them. And then we check the formal charges. So if you go through this whole thing, we're going to find that nobody has, they all have a charge of 0, and that's good because we want to get the lowest numbers possible. So this is probably a good structure for this guy. If we did the Lewis structure this way, we would have formal charges on this oxygen and this oxygen. So this structure is probably not correct. And after we do the Lewis structure, then we can start showing it as a condensed structure. When you get to organic chemistry, we're just going to start writing it like this because they get really long and complicated. So we start writing it like this. So this is called the condensed structure here in yellow. And we can have, when we draw a structure, and if we can draw more than one structure, then we might have isomers and we might have resonance structures. So isomers can be molecules that are put together in different order. And organic chemistry has a lot of isomers. So here's some constitutional isomers. They both have the formula CH3NO2, but they're not connected in the same way. So these are called constitutional isomers because the way they're put together is different from each other. We can also have something called resonance, which means that the way the Lewis structure looks is not exactly the way it looks in real life. And because the Lewis dot structure is limited, we have to do something called resonance. So it's actually a hybrid combination of several Lewis structures because the molecule actually can remember electrons can move around a bunch, and so they can move so that the electrons are equilibrated between a lot of different atoms. So that's called resonance. So if something lacks an octet, we can put in that double bond or triple bond. So remember, nitrogen didn't have, wasn't set up correctly here. It wasn't filled in its octet, so we put in a double bond. I think I skipped, sorry guys. Let me go back to, so anyway, we had to do this, remember? We had to try different structures, and we had to look at the formal charges, and one was a good structure, one wasn't such a good structure. But actually, the electrons can actually move in the real molecule of methyl nitrate. And so sometimes it's in this format, and sometimes it can be in this format. But what we're thinking is, in reality, this electron cloud is kind of smearing between the two. And this structure, the way we have drawn the structure, is really, in real life, is a hybrid between these two structures. So every once in a while, sometimes the electrons can kind of move from one place to another and change the way where they are in the molecule. And so that's called resonance. So the electrons, like I said, are moving around. That's called being delocalized. They're not associated with one particular atom. They can move through the whole structure. And our Lewis structure, the way Lewis dot structures are written, is not really perfect for real life. So resonance means that a molecule actually has these electrons moving from place to place very fluidly, and they're not necessarily sticking to one particular atom in the structure. So resonance structures are really composites of several Lewis dot structures, and the electron distribution is moving fluidly from one atom to another. It's mostly staying in the more stable form, but every once in a while the electrons are moving, smearing around, and moving a little into a different form. So most of the time the molecule looks like this, but sometimes it looks like that. So that's called resonance. So ozone is a good example. It's got a Lewis structure of this, with the formal charges showing. If this was true in real life, this would be a short bond, and this would be a long bond. But in reality, both of these bonds in ozone are exactly the same length. So we know that the way we've drawn this is not correct. It's a limitation of the Lewis structure. So this actually, the electron cloud is smearing between these two places, and the bonds are exactly the same length in both places. It's like a average of 2 bonds here and 1 bond there. That bond length is the same from here to here and from here to here in real life. So the Lewis structures are limited in how we draw them compared to what reality is. So the structure really is an average between a double bond and a single bond in real life. The next thing is harder to deal with, the structure of the geometric structure of molecules. So this is something you really need to look at and think about, because it's going to take a while to understand the way we're talking about geometry and also the polarity of a three-dimensional molecule. This is a hard topic for most folks, so please take some time to really think about this. So when we talk about the geometric structure of a molecule, we're talking about the bonded nuclei of atoms that are bonded together. We're talking about the shape of the bonded nucleus of each atom that's hooked to something else. So if I have an atom hooked here, the nucleus there, a nucleus there, and a nucleus there, this molecule we call linear. If I have a nucleus here, and a nucleus there, with some central atom, then we're calling this central atom trigonal planar. So we're looking at the nuclei of different atoms hooked together, but we also have electron pairs that are not bonded to something. They also change the geometrical shape of molecules, so it gets confusing. So we got to know these names that I'm showing you here. There's a lot of different geometric shapes that we're going to be using, and we have to start getting used to them. So I gave you that packet to work on. So in methane, we have the central atom is carbon, and then we have 4 hydrogens hooked to it. Each one of these bond angles is 109.5 degrees. And so degree measures are important to try to figure out what the geometry is and also what the polarity is in molecules. So what we're talking about is just where are the nuclei and how are they attached to the central atom. So we're talking about a central atom and who's hooked up to him. Vespers means that all of the atoms in the molecule are pushing away from each other so that they can have as much space as possible away from each atom. So the hydrogens are all pushing away from each other so that they can have as much space in around them as possible, so they're not near another hydrogen atom. So that's called Vesper. Valence shell electron pair repulsion, we call it Vesper for short. And it looks at the bonded atoms and also the unshared pairs of electrons. So for example, water, you would think it would be linear because it's just a hydrogen, oxygen, hydrogen. But it's actually bent because over here we have electrons that are in three-dimensional space and they're pushing down. They need space to live, to be in, and they're pushing the hydrogens closer together. So that makes water a bent molecule. So we've got these unshared pairs of electrons that are taking physical space in 3 dimensions. And when we talk about the shape of a molecule, we just talk about the bonded things together. So this shape is bent, even though we have these electrons hanging out here in space. Ammonia, same idea. It's got an unshared pairs of electrons. It's pushing these hydrogen atoms down. So it's changing that 109.5 to 107. This little molecule has no unshared pairs of electrons, so it's flat in 3-dimensional shape. It's planar, which means it's in one plane, and it's got a trigonal planar shape. So 120 degrees makes maximum space between each of the fluorines. We can also have double bonds and triple bonds, and they also take up space. So, for example, this double bond takes a lot of space. Electrons are in this area, so it's going to push this hydrogen down. Here's a linear guy. Carbon dioxide is linear. We're just talking about the bonded things that are bonded, the nuclei. What's that shape? Water has the bent shape. Now, after you know the shapes, then you have to figure out the polarity of the whole molecule. So remember, electronegativity, we talked about this when we bonded, is that number, that electronegativity number from the periodic table that we have to give you, and then we figure out which atom is more electronegative, who wants to get the electrons, and who's more electropositive, who wants to give away the electrons. Here's all your numbers. Remember, we're going to give you that Pauling number and the fluorine's the most electronegative. So the greater the difference in electronegativity, the more polar the bond is. And we said around 1.67, 1.7, we're going to call ionic. So we're talking about polar covalent bonds right now. The greater the difference in the numbers, remember, the more polar the bond is, the more polar covalent it is. So if we put these molecules that have differences in electronegativity in a magnetic field, they're going to line up. That's called a dipole. So to figure out who's going to have the electron cloud towards itself, it depends on the electronegativity. Who's more electronegative? You know, the fluorine and those guys on the right-hand side are more electronegative. So this is showing you how things are hooked together and which one has more of a more electronegativity difference. And that dipole moment is the amount of difference between the two and what's going to happen when they're in a magnetic field. So, to have a molecular dipole moment, we were just talking about between two atoms if they had a dipole. If a molecule has a dipole, then it's got to have one side that's more electronegative and one side that's more electropositive. So it depends on the polar bonds, and it also depends on the shape. You can have molecules that have polar bonds, but because of the three-dimensional shape of it, it's non-polar. So you have to look at two things. You have to look at polarity bonds and also the shape of the molecule. So it's a lot to think about. So really focus on this and pay attention to it. It's really important. So in this molecule, there's a little dipole that, remember this little sign saying the electrons are pulling that way, and this is more negative side, and this is more positive. But because these are 180 degrees apart from each other, that this molecule does not have any dipole moment to it. The bonds do, but the molecule doesn't because they're compensating for each other. So in this molecule, there's no dipole. So carbon tetrachloride has 4 carbons here. I think 1 carbon and 4 chlorines here. All these bonds are polar, but because of the three-dimensional shape, it has no dipole. This one, however, dichloromethane, has 2 chlorines and 2 hydrogens. So this molecule has a dipole. This side is very electronegative, and this side is electropositive. So the positive side, partially positive, is partially negative. So this molecule as a whole has a dipole moment. It's polar. So we can either say it has a dipole moment, or we can say it's polar. So this slide is showing you that. No dipole here because they're all counteracting each other, so carbon tetrachloride. But dichloromethane is different because it's got one side that's electronegative and one side that's electropositive. So that's the end of this slide lecture. This last part is really, really important, and it takes a while to understand. So please take your time and start learning the geometries and also what molecules are polar, which are nonpolar. Thanks for listening.